Hello, I welcome you all to this another interesting screencast, and the problem reads: determine the surface area of the concrete seawall excluding its bottom, and also a circular seawall is made of concrete. It's a continuation. Determine the total weight of the wall if the concrete has a specific weight of gamma subscript C or gamma concrete equal to 150 pounds per cubic feet. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So we have been asked to determine the surface area as well as the volume, which will later on help us to determine the total weight using the unit weight or specific weight of concrete that has been given. We are going to use the theorems that were developed by Papas of Alexandria. Alexandria, I understand, should be a city in Greece. Papas developed this theorem in the 4th century. Okay, Papas of Alexandria. Okay, and then this same theorem was reinstated, or it was stated again, or rediscovered again by another person in the 16th century, and his name was Gidnas. Okay, Gidnas, right? Have I pronounced the name correctly? I hope so. Gidnas, right? And so the two developed the theorems, which I think are the foundation of the formulas that we see right now for defining the surface area as well as the volume of any object. So those are the two theorems that we want to use, and the theorems are expressed as follows: for total surface area of an object, so surface area is equal to theta, which is the angle in radians, times the summation of the product of r curled by the length. So in this case, this can apply for an object that is just defined by a single curve or a combination of curves called a composite, a body defined by composite lines. So we can define this, we can calculate the total surface area by using this formula. And if we are dealing with volume, we are going to be using this formula. Volume is equal to theta, a summation of the centroid, the location of each area. So this is another formula that we can use for volume, where theta is in radians. So these are the two formulas that we are going to use to compute the surface areas as well as the volume. If you need more details about Gidnas and Papas, I did a video, I think a previous video of question number, I think 9-92, which maybe I'm going to show a link in this particular video. So I did a video. If you want more details about that, then you can click on that link that I'll give in this same video, so that you watch just the preamble of Papas and Gidnas. I had to draw curves, explained further, and so on and so forth. Right. So let's dive into the problem. So here we are going to start with calculating the surface area. So we need to redraw this particular concrete seawall. Mind you, we have been asked to define or determine the surface area of this concrete wall, excluding the bottom. All right, excluding the bottom. So the surface area should include everything, all this and all this, and the back as well as this part. We should not forget the sides. So the sides, we need to calculate them separately. The formula that we are going to employ will only calculate the top, the inner side, this area and the top, as well as the back side. It will not calculate the sides. So the sides we need to compute them separately, the sides. Okay. All right. That is for the surface area. For the volume, we don't need to do that. We just calculate directly. Volume captures everything. All right. So let's draw this quickly. Let's draw this quickly. We draw these particular parts and we begin to do the calculation. So there we go. I think we'll have something like this. Something like this. Okay. This is good enough. I think so. Okay. Let me bring it somewhere there. And then something like that. I need a straight ruler. Something like that. Something like this. Great. I think this is good. So I'll need to copy this so that I can also borrow it that side, and I can also take it that side. Okay, great. They are like so. So let's now fill in the information. We start with the surface area. So we have this point here. Okay, let's remove the bottom line. We remove the bottom here. We are not dealing with the bottom because we are using just lines. So the equation that we are using here is, let me create a boundary here because I'll need two spaces. I create a boundary in between. Okay, let me say like so. Okay, so I'm using the formula here. Area is equal to theta and summation of the centroid, the location of each particular component, where theta is equal to convert this to radians. So this becomes equal to 5/18 because 0 and 0 go pi. Okay, so that's our theta. So let's dimension this quickly. So we know that the top here is 8 feet, right? And the side here is, what is this? This is 30 feet. And this here, therefore, this here, okay, let me, so this here, this is 7 feet, this is 8 feet, and let's number this. Let's call this as my part 1. This is my part 2, and this is my part 3. These are lines, as in line 1, line 2, line 3. Okay, and let's define them. We need to define the length of each line. So let's say length of line 1 is equal to Pythagoras, right, of 7 squared plus 30 squared, right? Is that not so? Which gives us just the root of 949. Then line 2, its length is just known as 8 feet. Line 3, its length is known as 30 feet. Okay. So what else do we have? Let's define a area, which are the centroid, the location of which one. So this one, it will have a centroid location here, the other one there, the other one there. Okay. So we need to just name this. So start with this one here. Mind you, we are starting from the axis of rotation. There is an axis of rotation. Imagine we have the axis of rotation, which is this point here. See this point? There is an axis of rotation here. Okay, there is that axis of rotation. You don't forget that. So for us, we'll bring it somewhere there. Let's bring it somewhere there, like so. All right. So this is our axis of rotation. This is the axis of rotation. Okay. Okay. So let's define this distance here from there to there. Define this distance. Let's define this distance. Let me use blue. This one there, from there to there. Okay. So we know that here from there to there, this is going to be equal to 3.5, right? It's going to be equal to 3.5. Okay. So therefore, our area curved by 1 is just going to be equal to 3.5 plus 7. I mean 60 rather. 60 plus 7. This distance from the axis of rotation. 60 plus 3.5, and it gives us a 63.5, right? So 60 plus 3.5. Okay, because this distance here, this one here is 60. Okay, is that fine? Great. Then let's define the center for, this one here, R2. This one there is R2 is going to be equal to, that's 4. This length here is 4. So this length here is 4. So it is 4 plus this length here up to there, we already know it. It is 7. Okay. So it is 4 plus 7 plus 60. Okay. So what is 4 plus 7? That's 67 plus 4. That is 71. So this is going to be equal to 71. And then finally, this one at the very end. Here. So R curved 3. This is going to be equal to that is 60 plus 15. Okay, 60 plus 15, right? What is 60 plus 15? That is 75. Okay, so we have everything here. So what we need to do now is to do the calculation quickly. So we use the table. We can use the table. Okay, I think the table is good. So we have part, and then we have R curved in meters. Then we have a length in meters also. Then we have the product of phi theta, that's 5 pi by r squared by L. Okay, let's draw the table. Let's draw the table. Okay, I think let's use another color. It's like we are running out of space. Okay, this is not good enough. There we go. Something like this. Alright. There we go. How many parts do we have? We have one row, the second one, the third one, and the fourth thing for summation. Okay. I think this is good enough. This is fine. We can go ahead and fill in the table. Alright. So what do we have? We have part 1, we have part 2, we have part 3, we have summation. For R1, we said R1 is 63.5, R2 is 71, R3 is 75. The length L1 we said is just root of 949, and then for part 2 we said is 8, part 3 is 30. And then when we multiply 5 over 18, which is theta, the angle of revolution, we just went 50 degrees rather, times the centroid or position or location, which is perpendicular to the axis of rotation, then times the length. Then we find a 170.0813, right? Of course, 63.5 by root of 949 times 5 divided by 18 times 1707081 Great. Then we do the product for the second one. Second one we have a 495.6735. The third one we have a 1963 point. Let me calculate again this one. 71 by 8 by 5 over 18 by 495.667.35. Great. And then 75 by 30 by 5 over 18 by pi. So 1963.4954. Okay. So when we sum up everything, we have an area of 4166.25, right? 1707.0183 plus 495.6735 plus 1963.4954. 4166.25. Great. So call that as our area 1. We need the surface area also. So let's say our area 1. We found it as 4166.25. So let's find our area 2. Our area 2 therefore is going to be equal to, the surfaces is 2. These are trapezoids times half a plus b, a plus b, which is 15, then times the height 30. Remember the formula for trapezoid. So when we work out this 8 plus 15 times 30, we have a 690. So our final area, therefore, the total surface area is equal to A1 plus A2, which is going to be equal to 4166.25 plus 690. This gives us 4166.25. This gives us a 4856.25 feet squared. So that is the first part. The total surface area, we found just the first part. This is the total surface area for the first part. So surface area equal to 4856.25 feet squared. So this is the surface area. Okay, this is the surface area. So we need to find the rest. Let's find the volume. This is the surface area, excluding the bottom of the wall. So let's find the volume. I think we'll move this a little bit up like so that we have some space. We'll move this up. So for the volume, we'll divide this into two parts. So we'll bring this somewhere there like so. Let me use black. There, something like that. All right. So we'll call this as our part 1, and then this one our part 2, and then that is our height, which is height of the wall, 30 feet. Of course, that is the other dimension on top there, 8 feet, and this one there we said is 7 feet, and this one there it is 8, and the total of course is 15. Okay, so if we are to define, let's start with the area quickly. Area 1 is half times 7 times 30. So this becomes 0.5 by 7 by 30 is 105. That's area 1. Area 2 is just 8 by 30, and this is equal to let me move this this is just 240, right? This is 240. So we found the areas. Let's find the centroid location. So for this one is a triangle. Let's not forget to draw the axis of rotation. It will have the axis of rotation also, let's say somewhere here. We don't forget that, the axis of rotation, and the axis of rotation from one end, from there to there, it is 60 feet. Okay, so there we go. We have this one at the center, this one at 1 2/3 from the start. So let's say we have something like this. So we have from there to here. So this distance here, let me show something. This one here, from here to here, this one is 2/3 of 7, right? 2/3 of 7, right? So we are summing it up with 60, right? We are summing it up with 60. Therefore, our R1, our R code 1 is going to be equal to 2/3 of 7, 2/3 of 7 plus 60 gives us a 64.6666, so we can write down to 67. So that's one centroid location. Then the other one is just half. You know that half the length there, just this part there, half the length of that is 4. Okay, and then later on you have from this point here to there, this is 7. Okay, and then there you have a 60. So it's 7 plus 60 plus 7, which is 67 plus 4, which is a 71, right? So we take this one down like so. We draw a line, which is our centroid location. This one is equal to 71 feet. So we draw a table in like manner quickly also. So we have part, we have area curled in meters, area curled in meters, and then we have L in meters, area in meters, and then we have 5/18 pi area curled area. Okay, so let's draw the table. Let's draw a table quickly. Great. So how many parts do we have? We only have 2, so we have 1, 2. This one is too small. 2, 3. Great. So there we go. Let's fill in this table quickly. What do we have? We have volume. So part 1, 2, then summation. Part 1 is area centroid position is 64.67, and for 2 it is 71, and then for the area, area 1 is 105, area 2 is 240, right? And then if we do the calculation, the product there of 64.67 by 105 by 5/18 by pi, this gives us a 5925.6982. Okay, then this other one we get a 14,870.2052. Then the total, we have a 2795, a 2795.90. Okay, so that's the volume. So I can say the total volume Okay, the total volume V is equal to 20795.90 cubic feet. But they told us that we are supposed to find the total weight over the concrete. So total weight W will be equal to volume by the unit weight. So when we multiply 20795.90 times the unit weight was given as 150, right? In the, you see this one here 150 pounds per cubic feet. That's the total unit, that is the unit weight of our concrete. So by 150, so what we get finally is W is equal to, if you multiply that 20795.90 by 150, okay, we'll have a large value which I'll just write using this notation. It will be 3.12 times 10 to the power 6 pounds. Okay, so that is the total, that's the total weight of concrete. Okay, can I put it here, down here? Okay, I put it there. So in blue I say weight of concrete equal to 3.12 times 10 to the power 6 pounds. Okay, so that is the final solution. That is the final solution, and I hope the video is helpful. And if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.